Okay, in this video we define cut set, fundamental cut set and fundamental circuit in a given graph. So let me start by defining a cut set. So in a connected graph G, so a cut set, it is going to be a set of edges whose removal from the graph leaves the graph disconnected. Okay, so set of edges whose removal leaves the graph disconnected, but it must satisfy one more property, provided the removal of no proper subsets of these edges disconnect G. Okay, then such a set is called a cut set in a graph. So let me repeat the definition. So a cut set is a set of edges whose removal disconnects the graph, whereas if you remove a proper subset of those vertices, then the graph will still be connected. Okay, proper subsets, removal of proper subsets, it won't disconnect the graph. Then such a set is called a cut edge. Okay, so let's look into this graph G. Okay, here we can see that, okay, let's consider this set E1, E6, okay, E1, E6, E7 and E5. So let's remove these edges from this graph. So let's call this this set yes. So if I remove these edges, okay, we get, so what we are doing is we are removing these four edges from the graph. Okay, now we can see that after removing these edges we get this graph, a disconnected graph, which looks something like this. So it has these three vertices, and here we have this connected component C and one more B. Okay, so this is F and one more edge P. Okay, so here we can see that if you remove these edges from this graph, the graph will become disconnected, and moreover we can see that it do satisfy this property. If you consider any subset of these edges, for example, if you consider say E1, okay, removing E1, it won't disconnect the graph. Similarly, removing E6, it won't disconnect the graph. Okay, similarly with E7 and E5. Okay, so those are one element proper subsets of this set. So let's look into two element proper subsets, E1, E6. So if you remove E1, E6, okay, we can see that the graph is still connected. Okay, and similarly you can see that E1, E7, if you remove E1, E7, okay, again the graph is still connected. Same with E1, E5, and similarly you can see that if you delete E6, E7, okay, E6, E7, still the graph is connected because we can reach all these vertices through this E1 or E5. Okay, similarly you can see that E6, E5, okay, if you remove that, the graph is still connected. Okay, and similarly with E7, E5, etc. And if you look into any three subset, again you can see the same kind of situation. So for example, if you take these three edges E1, E6, E1, E6, E7, again we can see that the graph is connected. Okay, we can reach the other portion, okay, this portion by using this edge E5. Okay, similarly you can also see the same kind of situation with E6, E7, E5, E6, E7, E5. Okay, we can read through this E1. Okay, and similarly you can also verify that, okay, if you consider any three element subset, okay, and you delete those edges from this graph, the graph will still be connected. Okay, so that says this particular set, okay, it is a cut set. Okay, so if you remove these edges, the graph will become disconnected. Okay, something like this. And again we can see that no proper subset, deletion of no proper subset disconnects the graph. So we can see that is true with this particular. Okay, and again we can see that if you consider this set E9, okay, so if you delete this E9, again we can see that the graph will become disconnected. We have this component and this component. Okay, and again it is a singleton set, so no proper subset. So this is also a cut set. Okay, whereas okay, if you look into this particular thing, say E9, E1. So if you delete these two edges, E9 and E1, okay, we can see that the graph becomes disconnected. Okay, but the thing is that here we can find a proper subset. In this case E9. Okay, if we delete E9, the graph will become disconnected. Okay, so provided removal of no proper subset of this edges disconnects G. Okay, so this is this set, it is not a cut set. Okay, so that's the definition of what a cut set is. So a cut set is a set of edges whose removal from the graph leaves the graph disconnected, provided removal of no proper subsets of these edges disconnects G. Okay, so okay, these two are examples of cut sets in this graph, whereas this is an example of a cut as okay, cut in the graph. Okay, that is not a cut set, because here we can see that if you remove E9, okay, the graph is still connected, so it doesn't satisfy this condition. Okay, removal of no proper subsets, okay, disconnects G. Okay, so let's look into the same graph and find all the cut sets in this graph. Okay, and we saw this E9 is a cut set. So E9 is a cut set. Okay, similarly you can see that okay, we saw this one also, right? E1, E6, E7, E5, it's a cut set. Okay, and similarly you can see that if you consider these three edges, E1, E6, E8. Okay, that is also a cut set. Again, you can see that okay, if you remove this one, the graph will become disconnected. We have this connected component and this connected component. And similarly, okay, and again you can we can see that if you remove any proper subset, okay, E1, E6 for example, okay, E1, E6, the graph is still connected. E6, E8, the graph is still connected. E1, E8, the graph is still connected. Okay, so that is also a cut set. Similarly, these three edges, so E8, E7 and E5, okay, that is also a cut set. Similarly, okay, this one, these three edges, E2, E4 and E5, okay, these three edges are also cut is also a cut set. Similarly, okay, these three, so E1, E3, E2, okay, it's also a cut set. And I think okay, so if you consider this portion, okay, so this set E1, E3, E4, E5, okay, these are some examples of cut sets. Okay, so these are some cut sets in this graph D. Okay, similarly you can also find another cut sets like E2, E3, E6, E8, okay, another one like E2, E4, E7, E8. Okay, so okay, now the definition is clear, I think so. A set of edges whose removal from the graph leaves the graph disconnected, whereas the removal of no proper subsets of these edges disconnected G, then such a set of edges is called a cut set. Okay, so another way of looking at cut set is as follows. Okay, so let's consider a particular cut set, say E1, E6, E7, E5, E1, E6, E7, E5. So we saw if you remove this particular set of edges, okay, from this graph G, okay, we get this disconnected graph. Okay, so here we have this connected component containing these three vertices and those edges, and this one BF. Okay, here we can see that if we collect the vertices here on this first component ACD and collect these three vertices B, E, F. Okay, here we can see that if we take the union, we get the entire vertex set A, C, D, and again we can see that if we take the intersection of these two sets, we get null set. Okay, so that says, so a cut set, it partitions. So partition means if, okay, when we take the union, we get the entire set, and if we take the intersection of those two sets, we get null set. Okay, so a cut set partitions the vertex set, okay, in such a way that one endpoint of the edges one endpoint of the edges one endpoint of the edges in the cut set is in the first partition and the other endpoint is in P2. Okay, so okay, in this case we can see that here the cut vertices are E1, E1, E6, E7, E5, and here we have these two sets V1 and V2, a partition of V. So here we can see, if we consider E1, one endpoint, this A is in V1 and B is in V2, and similarly if you look at this edge E6, okay, one endpoint is here, another endpoint is in the other set. Okay, similarly with E7 the same thing holds. Okay, and E5. So this is another way of looking at the cut sets. So a particular cut set, it partitions the vertex set into two in such a way that the first partition corresponds to the induced subgraph of the original graph, okay, and another one corresponds to an induced subgraph of the other one, okay, in such a way that if you consider a vertex an edge in the cut set, okay, one endpoint will be in one set, say V1, the other endpoint will be in the other set V2. Okay, so this is another way of looking at the cut sets. Okay, and again we can see that if you look into a particular tree, okay, so if you remove any edge, okay, we can see that the tree, so this is a tree, okay, let's call that tree T. So here we can see that, okay, if you look into any edge here, and if you remove any edge, okay, this graph will become disconnected. Okay, so that's the tree, and that says removal of any edge from a tree breaks it into two parts. Okay, so every edge of a tree is a cut set. Okay, so removal of any edge from a tree, okay, it breaks or disconnects the tree into two parts. Okay, so we can see that every edge of a tree, okay, is a cut set. Okay, so that's the definition of what a cut set is. So let's look at the definition of what is called a fundamental cut set. Okay, so the fundamental cut set is defined with respect to a spanning tree. So let T be a spanning tree of a connected graph G. Then the cut set formed by exactly one branch, okay, of T and possibly some more chords of T, okay, is called a fundamental cut set of G relative to the spanning tree. Okay, let me repeat the definition once more. Okay, so let T be a spanning tree of a connected graph G, then the cut set formed by exactly one branch. Okay, so this particular cut set, it is going to have, okay, one branch and possibly some more chords of T, okay, is called a fundamental cut set of G. Okay, so let's look at this graph. Let's call this graph G. Okay, first let's find a spanning tree for this graph. Okay, so let's consider this spanning tree, which I am going to highlight with this blue. Okay, so we have this spanning tree highlight in this green color, T. Okay, then a cut set formed by exactly one branch. So that says, okay, a cut set, it must contain exactly one of these, E2, E3. Okay, so here the branch edges, okay, or E2, E3, E2, E3, E5, E2, E3, E5, E8 and E9. Okay, exactly one branch, say B of T, and possibly some more chords of T. Okay, so here the chords of this spanning tree are, okay, with respect to the graph is, okay, these non-branch edges, E1, okay, E4, E6, E4, E6, E7, okay, E7, that's it. So here it has 1, 2, 3, 4, 5 branch edges. Okay, this graph has 6 edges, 6 vertices. Okay, it's okay, and total 1, 2, 3, 4, okay, 5 plus 4, 9. Okay, so these are chord edges. Okay, so a cut set formed by exactly one branch of T and possibly some more chords of T is called a fundamental cut set. Okay, so let's look into this particular graph and this spanning tree. And okay, here we can see that, okay, if you consider this cut set, okay, that includes E4, E5, E4, E5 and E6. Okay, let's consider this set, E4, E5, E6. So if you look at this particular edge set, we can see that if we delete that, okay, these edges from this graph, we can see that the graph will become disconnected. So we have this component and this component, and again we can see that, okay, it do form a cut set in a proper subset, it won't disconnect the graph. And again we can see that if we look into this particular set, okay, E4 is a chord edge, okay, E5, okay, it is a branch edge, so this corresponds to B in this definition, okay, and E6 is a chord edge. So exactly one branch, so it's a cut set and it contains exactly one branch and some more codes. So this is an example of a fundamental cut set. Okay, so whereas if you look into say this, okay, this set E okay, E8 and E9. Okay, so let's look at that. Okay, these two edges E8, E9. So if you delete these two edges, the graph will become disconnected. And again, we can say that if you delete any subset, that is if you delete only E8, then the graph is still connected, and if you delete only E9, the graph is disconnected. So it is a cut set, okay, whereas it is not a fundamental cut set, because here we can see that these two edges E8 and E9 okay, both are branch edges. Okay, so it is not allowed in a fundamental cut set. Okay, so the fundamental cut set, okay, it is a cut set that is formed by exactly one branch and possibly more chords, okay, of a spanning tree. Okay, so this is a fundamental cut set. This is not a fundamental cut set because it contains two branch edges. Okay, so okay, let's look at the same graph G, and let's find say some more fundamental fundamental cut sets of this graph with respect to each branch. So let's find say fundamental cut set, say determined by say E2. Okay, so in this case, so that says E2 is the only branch edge that belongs to that cut set. So if E2 is there, then what we can do is we can put E1. Okay, so we can see that this set it is a cut set, and again it contains only one branch edge, in this case E2. Okay, so that is a fundamental cut set. So whereas okay, if you look into this particular thing, E2, E3, E5, E6, that form a cut set, but it is not a fundamental one because it has many branch edges. Okay, so let's find a cut set in which a fundamental cut set in which E3 belongs. Okay, so if E3 is there, okay, then we could consider these three. So that corresponds to E3, E1 and E4. So we can see that okay, this is a cut set, and furthermore we can see that it contains only it contains exactly one branch edge only. Okay, so that is also a fundamental one. So okay, that is determined by this E3. Okay, so let's consider E5. So E5, okay, it means okay, we can consider this one, right? E5, E4, E6. Okay, this set is a cut set and it contains exactly one branch edge, in this case E5. So let's consider a fundamental cut set that includes E8. Okay, so E8, so it means okay, it corresponds to this particular thing, E8, E6 and E7, and I think one more, okay, E9. So we can add these two to this set. E9, E6 and E7. Okay, so these are the different fundamental cut sets, okay, in this graph, okay, determined by, okay, these branch edges. And again here if you look into these fundamental cut sets, we can see that, okay, every branch of a spanning tree defines a unique fundamental cut set. So we will prove this in a future video. Okay, that is one important thing related to a fundamental cut set. So every branch, so let me write down that particular thing. So every branch of a spanning tree uniquely determines a fundamental cut set. Every branch of a spanning tree uniquely determines or defines, okay, defines a unique fundamental cut set. Okay, so that's what we saw from this example. So we will prove this in a future video. Okay, so the definition is clear. A fundamental cut set, let T be a spanning tree of a connected graph, then a cut set formed by exactly one branch of T and possibly some more chords of T is called a fundamental cut set of G relative to spanning tree. So that says if you take a different spanning tree, so in this case we can say that if you look at this graph, we could have many spanning trees, and with respect to a particular spanning tree we define what is called a fundamental cut set. Okay, so if we take a different spanning tree, we will get a different set of fundamental cut sets. Okay, it may not be equal to these. Okay, this is, okay, these fundamental cut sets are with respect to this spanning tree. Okay, so that's the definition of a spanning tree. And I think one more definition is remaining. What definition of what is called a fundamental circuit. So it is defined as follows: let T be a spanning tree in a connected graph. So it is also defined with respect to a spanning tree. So here we can see that when a chord, so okay, that is true for any tree. If you add one more edge to a tree, then we will have a cycle. Okay, so okay, this particular definition is related to some something like that. Okay, let T be a spanning tree in a connected graph. When a chord is added to a spanning tree, then it forms exactly one circuit. So such a circuit is called a fundamental circuit. Okay, so here we can see that, okay, here the chord edges are E1, E4, E6, E7. Okay, that's it. So these are 4 chord edges, and let this be a graph G, and the spanning tree is highlighted here in green. Okay, so in this case we can see that if we add, say, so if we add a chord edge E1, okay, so if we add a chord edge, we can see that, okay, we have a cycle here. Okay, and similarly we can see that if you add E4, okay, then we get a unique cycle, and the same thing is with E6 and E7. So that's what a fundamental circuit is. Okay, so when a chord is added to a spanning tree, then it forms exactly one circuit. Okay, and such a circuit is called a fundamental circuit. Here we saw if we add this E1, okay, in this spanning tree, then we have this circuit, and if we add E4, then we have this circuit, and similarly if we add E6, then we have this circuit or cycle, and if we add E7, we have this circuit or cycle. And again we can see that, okay, each chord uniquely defines a fundamental circuit. So if we add E1, we get this circuit, and if we add E4, then we get this circuit, and so forth. So each chord edge uniquely determines a fundamental circuit. Okay, so let me write down. Every chord of a spanning tree. Defines a unique fundamental cycle or a fundamental circuit. Okay, so that's for this video. So in this video we saw the definition of a cut set, fundamental cut set, and a fundamental circuit. Okay, in the next few videos we are going to prove some properties of these cut sets. Okay, and while proving that properties, we will also discuss the relationship between those and fundamental circuits. Okay.